Okay, so let's get started. Okay. So as you know, there's an exam this Thursday. I mistakenly said Friday last time. It is Thursday. It hasn't changed. Okay, it's still scheduled for Thursday. I will put up the review guide later today. I had planned to do it over the weekend, but I got a little delayed. It's almost ready. I'm going to work on it a little more and post it later today. So it should give you a good sense of all the concepts you should know to study for the test. Okay, test will be very somewhat similar to last time in terms of length and types of questions, mix of questions that ask you about a concept and ask you to apply a concept to some simple scenario. Okay, very similar type problems, but the study guide should also help you figure out what concepts to study for the test. Yes, question. Will there be a review session? I had not planned to do one. If it might, I will see if the TS can provide some extra help. If once the study guide is out, just look at it and we can try to do something. Okay. Any other question? But we are always here to answer questions. So if something is not clear, you should come by and ask. There are daily office hours, as you know. Right? Okay. The other announcement I wanted to make was I am going to give a lablet on cloud computing, because the lab that you already have, which I don't know if anyone has looked at it, but there's a component in the lab that requires you to deploy whatever code you're going to develop in lab 3 on the cloud. Okay, and we will give you credentials for the cloud. That's going to come as part of a lablet where you will try to do some basic things, and then you can use the same credentials to deploy your application in the cloud. That way you don't have to pay for any cloud resources or anything like that. You will get a student credentials that gives you some free access. Okay, so keep an eye out for that. Needless to say, this is going to be due after the test, but I'm going to hand it out in the next day or two so that you have it whenever you are ready to work on your lab. Start with the lablet, understand the cloud part. All right. Okay. So, one more announcement I wanted to make. The announcement previously had said that the exam 2 has material from lecture 8 through 16. Okay, that's what's posted there. The scribe notes for 16 are not yet there because the scribe hasn't given it to us. So I just decided to simplify things and not include lecture 16 on exam 2. Okay, so you have one less lecture to worry about. So only 8 through 15, and I'm going to send an email with all this information, but I thought it might be just easier not to make people study at the last minute, since we didn't provide the notes. Actually, it's not us, the scribe hasn't provided it to us, but be that as it may, you don't have to worry about it now. It will still be on the final, okay, but not on exam 2, right? Okay, so just to, so whatever we did last time is also not on the test. It's 1 week from today is what you have to worry about, right? So as you remember, last time we were talking about distributed transactions, concurrency control. And I talked about pessimistic concurrency control, which essentially uses locking to ensure that multiple queries can run in parallel, but they can figure out when there are conflicts and then abort and so on. Okay, so I started talking about one approach to do this, which is two-phase locks. I'm going to explain this, then I'm going to show you how you can combine this with this notion of timestamps to figure out when there might be a conflict and then roll back and whatnot, right? So, okay, so here is a scenario where you can assume that there's a transaction, okay, and the transaction is executing. In two-phase locks, okay, the lock manager essentially has to grab locks on data items as the transaction is running. The transaction accesses a data item X or record X in the database, you have to first grab a lock on it, okay, and so on. That way, once you started accessing that data item, other transactions are blocked from accessing it. Okay, so that's the basic idea. And in two-phase locks, the reason it's called two phases are there are two phases in this process where when the transaction is executing, there's something called the growing phase. which is when you keep acquiring locks. So the y-axis here is the number of locks you acquired. So each step represents grabbing of an additional lock by that transaction. Okay? Each time you access a new data item, you grab a lock on that transaction. Okay? So at some point in time, the transaction may have reached a point in its execution where all the data item it needs to access are already been accessed at least once. So it has a lock on all of them. Okay? That's this point in time. It's shown by the dotted line. And at this point on, you are not going to acquire any new locks because everything you touched within the transaction has already been accessed at least once. So it's time to then figure out when you are going to start releasing locks. Okay? So as you're done with accessing each data item within that transaction, you can start releasing locks. So that's the shrinking phase. So the first phase is called the growing phase, where you acquire locks. In the shrinking phase, you start releasing locks. Okay? So and that it's up to the transaction manager to figure out when that transaction is done accessing X or Y or whatever it is, even though the transaction hasn't finished, still executing, but it's done with X. So you can say, let's release X. The reason to release locks early, it increases concurrency. The longer you hold locks, the more you're going to block other transactions from making progress. They're accessing that same data item. Okay? So you want to start releasing these locks early in the shrinking phase. That allows you to increase the concurrency in the system. Okay? Now there's a variant of this called strict two-phase locks. In strict two-phase locks, as you can see, you do not start releasing them one at a time. You wait until the transaction has finished and then release them all at once. Okay? That's a simpler approach. The transaction manager does not have to figure out, is the transaction done with X or not, or Y or not. You just acquire locks as you access each data item. When the transaction is done, whether it commits or aborts, you just release all locks. Right? That's strict two-phase locking or strict 2PL. Okay? Two-phase locking is also known as 2PL. Okay? We will talk about two-phase commit in a little bit. Different concept from two-phase lock. Both have two phases, but then these two concepts have nothing to do with one another. Yes. So you're asking, is two-phase locking or strict two-phase locking easier than two-phase locks from rollback perspective? Is that the question? I don't think there is anything to do with rollback. It's just a matter of concurrency and things of that sort. Of course, there is one thing that might still happen is if this transaction releases a lock, another transaction grabs it, it might so happen that they have a right-right conflict. So it might reduce the chance of a rollback slightly. But in general, I think they will have similar properties, but there may be slight advantage to holding the locks all the way to the end, so there are no conflicts that are created. Okay. Let me now explain how you can decide if there has been a conflict between two transactions that are working on the same or an overlapping set of data items. You can do this very simply using timestamps. Okay? And these timestamps in this case can be physical timestamps. We don't really need to worry about logical timestamps. So the way this technique or this type of concurrency control will work is that each transaction will be given a timestamp when it starts, and that's the time at which it started. Okay. Now, if transaction I wants to perform an operation that conflicts with J, okay, transaction J, then one of these two have to abort because you're essentially having a conflict. And so what we are going to use is we are going to use a timestamp to figure out which one to abort. The one that started earlier actually has to restart, okay, because the later transaction has already touched something that this transaction is working on. So you give priority to a later transaction. Okay? When a transaction aborts, it must restart with a newer timestamp, which means a later timestamp when it restarts. Okay? So how are you going to figure out whether there is a conflicting operation? That's really the crux of the approach. And the way you're going to do this is for every record in your database or every file or a data item that you want to protect, you are going to maintain two timestamps with it. Okay? So there's a read timestamp and a write timestamp. Okay? So the read timestamp of a data item is the timestamp of the latest transaction that has read X. Okay? If transaction I reads it, and you take its timestamp, and then you can update it if it's a later. Okay? And the max write timestamp is the max timestamp of a transaction that is updated X. Okay? So this is the most recent read and the most recent write to item X. Okay? And then all you're going to do is do a very simple comparison. So if a transaction wants to read a data item X, you look at that transaction's timestamp and compare it to the max write timestamp, saying, is there been a newer transaction that's already modified this data item? And you are an older transaction. If so, you have to abort. Okay? That's what you say. Okay? If not, you're going to perform the read, and then you are going to update the read timestamp to the max of yours and the current max timestamp. Okay? So the conflict will occur. So this is called a read-write conflict. Okay? You are trying to read, but there's a newer transaction is already written. Okay? And since these two transactions conflict, okay, because neither transaction is finished, you are going to abort the earlier one. Okay? And then you have a similar check you want to perform if the transaction wants to do write. In this case, you want to check if a newer transaction has read the data item or a newer transaction has written the data item. So you check for both a write-write conflict, if you are trying to write and a newer transaction has written, or you also check for a read-write conflict. Okay? So just as you did before, if a newer transaction has read that data item, then in either of these two cases, you are going to abort. Otherwise, you're going to perform the write, and you're going to update the timestamp. Okay? So that's basically how you are going to check if two transactions are ever going to conflict. You basically see if there's some other transaction that's working on the same piece of data. If so, you will yield if you are the older transaction. You let the newer transaction finish because someone has to abort. In this case, your older transaction. Is this clear? Okay. So that is all we have for distributed transaction. What we'll do for the rest of today's class is consistency and replication. Okay. Don't know if you'll finish all three parts, but I'm going to start with replication, explain how replication works, talk about some well-known results in replication. Then we'll talk about consistency. Okay, this consistency models are somewhat abstract. Okay, they are more theoretical in nature, but it's good to know what they are, because when you're implementing any replication, you got to figure out what kind of consistency guarantees you want to provide. Okay, and we'll see that there's a range of consistency guarantees you provide. They will derive from these concepts. Okay? And the last part, we'll talk about something called eventual consistency, which is a very straightforward approach and widely used approach in consistency. And we'll see that really doesn't give you a lot of guarantees, but it does implement what is called eventual consistency through epidemic protocol. Okay? Let's start with replication. Okay? We already had looked at replication way back in the very first lecture when I was talking about why we need distributed systems, what are their advantages. I mentioned centralized, decentralized. I also said that you could scale the performance of a system by replicating it. Okay? And we talked about data replication, where any data item in the system is replicated multiple times. We also talked about compute replication, where any computation or any code is replicated multiple times. Okay? In your lab 3, you're going to do compute replication, at least probably have some data replication as well. Okay? Now, what is the advantage of replication? You have two advantages. You get reliability, number 1, and you get better performance, number 2. Okay? So what is the reliability advantage? Okay? You have two replicas of a data item. Okay? If the machine holding the first replica goes down, your data is still available on the second machine. Okay? You have only one copy of the data item in the system. Let's say there's only one database. Okay? That database server crashes. Your application cannot function anymore because the data is inaccessible. But if you have multiple copies, and if one copy is down, you can go and look at the data item on some other machine. Okay? So that's your reliability advantage. Okay? There's also a performance advantage. Okay? Because you have multiple copies in the system, you don't have to send all your requests to only one machine. Okay? You can distribute those requests across multiple machines, and then you get the benefits of parallelism. Because there are multiple machines in the system, you can get higher throughput. Okay? This is a reason why we replicate things like web services. Okay? You want to scale beyond the capacity of your single machine. You run your application and you replicate the data on multiple nodes, and then you scale up with the number of nodes in the system. Okay? So that's going to scale with the size of the system. You can also replicate geographically. Okay? When we get to the web chapter, you'll see that geographic replication is an important concept. Here you have multiple copies, but you put them in different locations. Okay? Maybe you have a copy in the Asian data center of a cloud provider, you have one in Americas, one in Europe. In that case, you send a client or a user to the closest copy so that the latency to access that data item is lower because you're going to a closer copy from a network distance standpoint. Okay? So many advantages, reliability, performance, and so on. Okay? Okay? And there are many issues as well. Okay? So you might ask, okay, when should I do replication? Is it static or dynamic? Should the number of copies be determined beforehand, or is it determined based on load? Okay? In case of cloud computing, okay, you can actually vary the number of copies as the load changes. Okay? That's called dynamic replication, also called auto scaling. We talked about that briefly early on. There's a question of how many replicas to create, where do you put those replicas, and so on. Okay? But we are not going to talk about any of these issues today. Okay? Today we will just talk about one issue, which is consistency. Okay? Whenever you have multiple copies of a data item, if you change one copy, the others are out of date. Okay? So you want to ensure, okay, that all copies stay in sync with one another. If one copy is updated, all copies have to be updated. Okay? This problem is called a problem of maintaining consistency. Okay? So it's an important problem in distributed system whenever you have any replication. Okay? Because if inconsistent copies, then your application may not perform as you want, because if some user gets an old version of that data item, okay, it might make some incorrect assumptions about whatever is going. Okay, so we want to make sure that all your copies stay consistent. If one copy is modified, how do you make these others consistent? Okay? That's what we are going to talk about. Okay? The problem of consistency clear. Okay? All these other things will come back to when we talk about the web chapter and so on. Okay? So before we talk in more detail about consistency, I want to introduce you to a well-known result in distributed system called the Cap Theorem. I don't know if anyone has heard of this theorem. Okay? So that's an acronym. Okay? CAP essentially means consistency, availability, and per partition tolerance. Okay? C for consistency, A for availability, and P for partition tolerance. Okay? So this was a conjecture that was made by Eric Brewer, who is a faculty member at Berkeley back in the year 2000. Okay? And the conjecture was that it is not possible for any web service or any distributed systems to provide all of those three properties simultaneously. Okay? You have to pick at most two of those three properties and give up the third one. For a fundamental reason, you cannot ensure that your system, if it's replicated, will be consistent. Okay? And if it's replicated, it will be available. Availability means that failure of some node does not take the system down. And partition tolerance essentially means that if there's a network partition, there's a network problem, that you can actually tolerate that network partition and tolerate messaging. Okay? So you cannot have all three properties. Okay? You can only have two of those three properties. So very well-known result in distributed system. You should at least know of this result. Okay? Because someday if you're designing any system and you try to achieve all of these two properties, you should know it's fundamentally impossible. So you shouldn't even try, which means that as a designer, you have to decide which two of those are more important for your application. Okay? Do you want to keep copies consistent? Do you want to make the system highly available? Do you want to tolerate network partition? If the network goes down, your things still, applications still work. Okay? So these are considerations you want to keep in mind. Now, although this was initially posed as a conjecture, there was a formal proof of this property that was presented in 2002. So now it's called the Cap Theorem as opposed to the Cap conjecture. Okay? So here are some examples. I'm not going to prove it, and this is really a theoretical proof, but you should know that the property is true. Okay? And so here are some examples of when you might pick two of these three properties. Okay? So first is, let's say you want your system to be both consistent, which means if the copies, there are multiple copies, they are in sync with one another, and it has to be highly available, which means if some nodes go down, they continue to function. Okay? So we have cluster databases where these databases are synchronized with one another. If some copy goes down, then you can still keep the others consistent and so on. Okay? So that gives you both consistency and availability. Okay? But it does not give us partition tolerance. Okay? So you might say, why? Okay? So let's assume you have a database cluster. Okay? And you slice the network in half. Okay? So some nodes are in one partition, one side of the network, other nodes are on the other side of the network. There's no connection between these two. So now you're in two separate parts of the network. Okay? So if you're doing things like transactions, it should be clear that that's not going to work, because you cannot have a transaction commit here and abort there and things like that. You want all your copies to be synchronized with one another. So you will not be able to tolerate network partitions in this case. But you can, so long as the network does not go down, okay, you can tolerate node failures. Okay, because if some nodes of the cluster go down, others are still functioning. That's okay. You can keep them consistent with one another, because when they're implementing transactions, they ensure that all the copies are synchronized and so on. Okay? That's an example of you have to give up one of the property to maintain the other two. Okay? And there are other examples. So if you want to do consistency and partition tolerance, you might have to give up availability. Okay? So we can think about things like distributed or pessimistic locking. To remember pessimistic lock, Rickert and Agarwala's algorithm. It said that you have to receive an yes from all the nodes to proceed. Okay? If there's a network partition, sorry, not network, node failure, means availability is being given up. If a node goes down, it does not respond, you cannot make progress, okay, for safety reasons. But if so long as nodes don't go down, you can deal with partition tolerance, because you can deal with consistency, right? And there is availability with partition tolerance, which we will get to when we talk about leases and web caching and so on. Okay? You don't have to understand all of these subtleties right now, but just have to get some feel for why it might be hard to achieve all three properties at the same time. You have a question there? Okay, all right. So that's a theorem, okay, and you will see this theorem shown as a picture with this triangle. Okay, triangle, just a pictorial depiction, doesn't have any more information. It says that you have these three properties. Okay, there is a lot of annotation here, which I'm going to ignore. But it basically says that you have to only get can get two of those three properties, okay, in any distributed system. Right? So that is all I'm going to actually say about Cap theorem. This figure specifically has some extra information about the so-called NoSQL databases. There are many databases that don't use relational or SQL model. They use their key value store databases. Okay, we haven't covered many of them here, but there are things like Dynamo, MongoDB. I've probably heard of some MySQL and Bigtable. So they all make different assumptions as to which of those two properties you want to achieve and which one you give up. Okay? So if you are using these databases for your application, it's good to know what properties they provide and what they don't provide, because the rest of your system is going to be locked into whatever those properties are. Okay? So these are things that you should know at a very high level at least. Okay? So having talked at a very high level about the Cap theorem, let's talk about things like replication. Okay? So this slide shows us object replication. We talked about distributed objects when we were doing RMIs, if you remember. Okay? So here we are now assuming that these objects that you have in your system, okay, are not just on one machine, they're replicated. Okay? This is not distributed objects, which means one object is on one machine and another object is on another machine. We're talking about taking an object in that level, such as a Java object, and actually having multiple copies of it. Okay? So you have this object multiple machines, so your code is also replicated on multiple machines. Okay? So there are two approaches for how you are going to do consistency, okay, in this case. Okay, the simple approach is that the system is not going to deal with it. It's done at application level. Okay? So that means if you want to have replicated object, you have to write extra code to make sure that if you call a method on an object, okay, and it executes on one machine, any update you make to the variables inside that object are sent to other copies of the object. This is something that you would have to write. That way you'll keep all the objects copies synchronized with one another. Okay? That's one option. Okay, the other option is that you can use a middleware layer that is going to handle this consistency issues for you. Okay, so when you, again, in this case, when you call a method on that object, the middleware will say, I need to make sure these changes are propagated to all of those. So there's a middleware sitting in between that's going to implement a replication and a consistency protocol. Okay, so you have two options. Most systems are going to punt and say, let the developer deal with this. Okay, and makes your job as a software designer harder. But then you can implement whatever consistency model you want on top of that. There are some other systems that are going to do this for you. Okay, later on in a few lectures, we are going to look at middleware systems, and I'll introduce you to some that will do this for us. Okay, both in Java and other languages. Is this clear? Any questions? Yes, question. Okay, so there's some, I glossed over this. So the question is, what do we mean by simplifies application development but makes object-specific solutions harder? Okay, so if you have a middleware system that's going to implement replication and consistency for you, you as a developer don't have to deal with it. Okay? You just decide, I want to replicate my code, and the middleware layer will deal with it. Okay? However, you are going to be locked into whatever consistency guarantees are provided by the replication scheme implemented by the middleware. Okay? In just a few slides, we'll see that although we would like to have consistency across replicas, there is no one approach to do this. There's a slew of approaches. Okay? So if you want a certain type of consistency guarantees, but the middleware provides some other consistency guarantees, you are then going to be stuck with whatever that middleware provides. So you cannot provide your object-specific approach, which might have done some differently. Okay? So essentially, it basically reduces flexibility because there's no one approach for consistency. There are a bunch of approaches. Okay? So that's basically what it's trying to say there. Okay, so let's talk a little bit about replication and scaling. Okay? We have not talked much about caching yet, okay? But there's a concept of caching that's like replication. Okay, caches essentially allow you to keep copies of frequently accessed data items in a easy to access or a fast access medium called a cache. Okay, caches also result in replication of the object, and both in caching and in standard replication, you have to implement consistency. Okay? And we'll come back to caching today. We're just going to talk about replication, but there is a question of under what scenarios are you essentially going to get good performance, and when what kind of consistency to provide, and so. Okay? So to understand that, let's take an example. Okay? So let's assume that you have some data item or an object, and you replicate it n times. There are n copies of this data item in the system. Okay? We'll assume that there are user requests coming into this data item, and this data item is read with the frequency of R and updated with the frequency of W. Okay? So it's read at a certain rate, updated at certain rate. Okay? Now, what consistency approach you pick actually matters with regards to what are the values of the read and write. Okay? For example, okay, if the reads are infrequent and writes are frequent, okay, you might actually end up paying a high consistency overhead. So I'll give you an example. Let's say there's a web page. Okay? Maybe it's your blog. You update it frequently, okay? But you don't have very many followers or readers yet. So not read very frequently. Okay? So now every time you update it, okay, you will have to then add a consistency protocol. Assuming you replicate this website on multiple servers, you have an additional consistency protocol which says, if I update this copy, send these changes to these other machines. Okay? That's our consistency protocol. So you keep updating and you keep sending these messages, which are consistency protocol messages to other machines. Okay? But no one is actually reading this blog as frequently, because we assume that in this case, the read frequency is much lower than the write frequency. Okay? So you wasted a lot of consistency messages because you're keeping these copies tightly synchronized, but you're not getting any benefit because after you send the update, no other user has come and read this object. Okay? So perhaps in this case, you might want to loosen your consistency guarantees and not have to send every update. Okay? But if the opposite were true, okay, which means you update an object once, but it's read many, many times, okay, it is a good idea to ensure that all your copies are synchronized tightly. Because as soon as you change something, okay, if the other copies are not up to date because it's being read frequently, you might get a read request, and then that read request gets an out of date version of your web page. Okay? So if the write frequency is high and the read frequency is low, which means that it's updated, sorry, the other way around. So if the read frequency is high and the write frequency is low, you can update it once in a while, but it's very popular, you might want to invest in a tighter consistency guarantee. Okay? So it's a very simple example that tells you that what semantics to provide actually matters. You might want to, in some case, provide looser guarantees, in some case, provide tighter guarantees, and so on. Okay? So variety of semantics are possible, and you have to really think about your system to understand what type of consistency guarantee makes. Okay? So we'll look at a bunch of these ideas. Okay? But it should be clear why we are talking about this at all, because you might think, why not provide the strictest guarantee possible always? Okay? So which we would call strict consistency or tight consistency, but it comes with a high cost. Do you want to pay that cost? And that's the question you want to ask. Okay? So let's start with how we are going to talk about this in the next several slides. So here's a picture that gives us the mental model of what is happening in the system. Okay, these disk-like things are 3 disks that have 3 copies of a data item. Okay, there's a process, okay, that is accessing each of these different processes, rather accessing each of these copy. Okay, processes can read that data item or update that data item. Okay, so our goal is, suppose some process makes a change to its local disk. How should that disk actually send those changes to this other disk so that these other processes, when they read it the next time, get the latest copy? Okay, so always our goal is that if some process tries to read the data item, you should try to send the results of the most recent update, because that's your latest copy in the system. Okay? But we'll see that sometimes what is the latest update is itself not clear. Okay? So there will be various semantics we want to provide. So let's start very simple. Okay? Strict consistency. Okay? So as the name suggests, every read that you make in the system, no matter at what replica, has to return the most recent updated version. You can never send an out-of-date version. That's what strict consistency means. Is that clear? Okay, simple idea. Okay. Now, easier said than done, because it's actually very hard to implement. Because strict consistency implicitly assumes that as soon as you make an update to any copy, it's instantly visible to every other copy in the system. Okay? Because that's the only way you are going to ensure strict consistency. So as soon as you change the data here, okay, all of these other copy or replicas are going to see that change. Okay, so you have to at least realize that that's physically not possible. Nothing can be made instantly visible. You can at most transmit messages at the speed of light. Right? So if you make a change to a copy here, you have to send a message, and that message is going to propagate at the speed of light. So it's not going to be instantly available at every other copy. So this is difficult to achieve so long as you can deal with speed of light. But that's the definition of strict consistency. Okay? This is extremely expensive to achieve. So we are going to keep loosening this requirement until we get to the very end of the lecture, where we have very weak guarantees. This gives you the strictest guarantees. So let's see how to keep weakening it one step at a time. And each step is going to give us a different model, a different type of guarantee you can provide in the system. Is that clear? Okay. So next is sequential consistency. Okay, this is weaker than strict consistency. So what this assumes, okay, is that, so now we are going to no longer say that as soon as you make a change, you see that change everywhere. Okay? We are going to weaken this and say, well, we can't do that because it's hard to do. So what other things can we do? So we'll say that we don't actually care about which order writes are coming in the system, because normally you say you send the results of the most recent write. So let the processes figure out some ordering of writes. Okay? Doesn't matter whether a write actually one write actually happened before the other write or not. You figure out what ordering makes sense, and we'll assume that's the order in which things have happened. Okay? Which might violate strict consistency, because you might say there is a write A and write B that happened in order A, B, but if the processes say they happened in the order B, A, we'll take it. Okay? Which means we will actually in some cases not give you the most recent. So here's an example. Okay? Or let me first define what this means. So we'll assume that first thing is that you have to always respect program order. Okay? If two writes are coming from the same process, you can't invert them and say that happened. So think of them as your print messages. Okay? So your print is a write to a screen. So if you are say one print message and another print message, they have actually happened in that order. You cannot say that they happened in some different order, because you cannot violate program order in sequential consistency. Okay? So first you respect program order, but so long as you do that, any interleaving is allowed. Okay? And all processes must agree on that interleaving. Okay? So let's say there are 4 reads and writes in process A and another 4 in process B. You have to respect the order of these 4 events. You have to respect the order of these 4 events, but you can say they interleave any way you want. You can basically move them back and forth. And so long as you have some interleaving, you're going to accept it as a sequentially consistent interleaving. Okay? And here's an example to make this a little more clear. Okay? So here we have 4 processes. Okay? So you have a write to A, which means you write A to X. Your process B writes B to X. So if this is time, you'll see that this write has actually happened before that write. Okay? Now these processes can decide, although that's actually the order that we see, the processes can decide either of those orders. You can say A, B or B, A. So long as they both, all of them agree, that's acceptable. Okay? So in this case, you'll see that when P3 does a read, it first gets B and then it gets A. Okay? So basically P3 is seeing these writes in the opposite order of what we are seeing in the picture, because these processes agreed on that order, and P4 also sees them in that order, and that is acceptable. Okay? In strict consistency, this would not have been the case, because once you've written B, all subsequent reads would have always received B. Right? So you would have gotten B and B in that case, but that's not what's happening. Okay? Now here is another interleaving. Okay? So this is legally acceptable as a sequential consistent ordering. Here's one that we will disallow. Okay? So here, same example, you have A followed by B. So you have written A to a file and then you wrote B to a file. Okay? When P3 reads it, it first sees B. When it reads a file, it gets B. When it reads that file, it gets A. So it's seeing them in opposite order. Okay? But when P4 sees it, it first sees A and then B. Okay? So now these 2 processes are seeing the writes in 2 different order. One is seeing BA, the other is seeing AB. That means you're not agreed on the interleaving. Okay? Because here both of them agreed that the write B has happened before A. That's what we agreed here. Even though that's not the case, that's what we agreed on, and that was okay. But here we don't see them in that order. So this is not sequentially consistent. This is going to violate sequential consistency. This is going to be acceptable from a sequential consistent standpoint. Okay? Needless to say, neither of these are strict consistency. In strict consistency, you always get the most recent write, which means that once this write has occurred, then you should have always seen B and B in all cases. Is this clear? Okay. So you might ask, why is it that these writes are showing up in 2 different orders? Okay. And the answer to that is that these replicas, they might be geographically far from one another. Okay. So assume that this one is in New York. Let's say this one is somewhere in California, and that one is far away. Let's say we put it off in somewhere in Japan or something like this, far from the other 2. Okay. So in that example I just gave you, let's say this replica gets written first. You write A here. Okay. And then this replica gets written next. You write B here. Okay. And then this replica does a read shortly after that. Because these are geographically far, the message from the first replica may not even have reached here before the message from the second replica reaches, because you are now different propagation latencies. So a later write might still reach a replica first. Okay? In strict consistency, we cannot let that happen, because we said the first write always has to be seen first before the second write. But in this case, we are going to let that happen because there are different propagation latencies. A later write might arrive first. So long as you agree, all processes see it in that order, we'll take it. Is that clear? Any questions on this? Yes. Okay, question is, wouldn't it be expensive to agree on one sequence? Yes, so thing you have to keep in mind is I'm just defining the concept. I didn't show how to implement the concept. Okay, so all of these protocols have a overhead, because in this case, you have to agree on that ordering. In strict consistency, you have to agree on the writes and make sure they're all visible instantly, which is not possible, but even so, you want to ensure that you never get something that's different from the order. So yes, the short answer is all of these have a cost associated with them. In this case, is agreeing on the order. And we'll see other cases where you have to agree on other things, but you will still have to implement a protocol that does that. Okay, and you can do other things like timestamping and whatnot, but that's what you will have. Right. So next one is linearizability. Okay, so this is going to be actually stricter than sequential consistency. So linearizability is going to sit between strict consistency and sequential consistency. So it's actually in between. So what it does is it will implement everything that sequential consistency does, but it has one more property which says that if a timestamp of x, logical timestamp of event x or write to x is less than the logical timestamp of y, then operation x should precede operation y. Okay? So basically it says as if two writes have a relationship with one another because the process sent a message between the two. There are one write here, one write, there is some message going between them, and then these two writes have become related. So then you are going to essentially, your ordering has to respect that ordering of timestamp. Okay? So this is going to be stronger than sequential consistency. Here is an example, okay, of how we are going to do this. So you have three processes, okay, three variables x, y, and z. You're going to assign x to 1, and then you're going to print y and z. Okay? So the way you want to see this, although this looks like code, this is really an abstract example saying this is a write to x. Okay? Print is going to be a read of y and z. Okay? So you have an x, and then you have these two data item y and z. So you have y equal to 1, and you print the other two variables, z equal to 1, you print other variables. And then the question is, what should the output be, and which outputs will we allow as linearizable and which ones not? Okay. So here are some interleavings that we are going to go with. Okay. So we'll assume initialize, they're all initialized to 0. So if you actually execute them sequentially, going to print 0, 0, 1, 0, 1, 1, okay, because that's the order in which you're modifying these things. Okay. And then you're going to do some other things and so on. Okay. So in this case, all of these execution sequences are going to be valid, because what has happened is as soon as you change something and it's been read, okay, all other processes are going to see them in timestamp order. Okay, and we'll take them. So it has to have sequential consistency, and you have to essentially have this timestamp order. Okay? So two properties that give you the combination. Okay? And I'm going to show you some other examples that make this linearizability a little more clear. Okay, so let's look at causal consistency, which will also give us some notion of how to do this. In this case, just causally related writes must be seen by all processes in the same order, but concurrent writes can be seen in different order. Okay? This is a weakening of sequential consistency. Here are two examples, one of which not permitted and the other one is permitted. Okay? So we have these two writes, you write A and then you write B. Okay? But there's a read between these two writes. Okay? So you write A, then you do a read, you see A, and then you write B. Okay? In this case, we are going to say these two writes are causally related, okay? Because this read is like sending a message from P1 to P2. Okay? I wrote A to a buffer, okay, or a data item, then I read that buffer. That's implicitly a message that went from P1 to P2 saying that's the value. Okay? So now these two writes in two different processes have become causally related. They haven't happened before relationship between them, because this read is acting like a message between each. To write to a buffer, then I read from the buffer. That's a message. I have basically communicated through a buffer with two processes. Okay. So in this case, the only ordering you can agree to are A followed by B. Okay. So you are not going to allow B to be seen first and A to be seen next. So this is disallowed. Okay. You have to see A, B, because that's the order in which things have happened. No, so we're not going to allow this as being causally consistent. Is that clear? Okay. However, if I remove this read, okay, which is the example shown there, okay, so I removed this. So now these two writes are no longer causally related, they are concurrent writes. In the context of logical clocks, these are independent events, they are not related to one another. They're independent events, you do not have to agree on an ordering. So it is okay for P3 to see BA and P4 to see AB. So they're seeing these writes in two different order, which previously we didn't allow, but now we are allowing concurrent writes to be seen in different order at different processes. Okay? But if they are causally related, we will disallow that. They have to have the same order. But if they're concurrent, they can have any order. You don't need to agree on it. Okay? This is called causal consistency. You maintain causal relationship between processes when you are trying to provide consistency guarantees. Okay? Is this clear? Any questions on this? Yes. Okay, question is, what is the causal relationship? A causal relationship is going to exist if two processes communicate. Okay, so just as we had in Lamport's clock, there is a message going from one process to the other. Okay, events in those two processes are going to become related. Okay? In the context of reads and writes, it's very simple. If you make a write, if you write to a variable, and then in another process you read from the variable, so this variable is acting as a shared buffer. Okay? So you write to this buffer, and then someone else reads to the buffer. That's like sending a message through the buffer from one process to the other. Okay? So once you send this message, okay, you are now essentially causally related. So here you have a write, read followed by a write. This read is causing these two writes to become causally related because you wrote and then you read that value here. So now you already sent a message. So any subsequent write is going to become causally related to this previous write. Okay? If that is the case, the order of these two writes has to be A followed by B, because as happened before, relationship between them. Okay? So that means every other process, okay, cannot see B and then followed by an A. They have to see them, these writes, if they are reading that same data item, you have to always see them in the order A followed by. Okay? Any questions? Yes. Yes. If question is, if P4 was BA, would it be wrong? It would still be wrong. Okay, you can only have P3 and P4 see AB. Okay? BA and AB is clearly wrong because they're seeing two different orders. BA and BA is also wrong because that does not respect that order. Okay? But AB is fine. And the only other thing I would say is, if you remove this read, then you can see them in any order. AB, you can see them BA, you can see them in two different orders with B and AB. All of those are accepted because there's no ordering. So you can say whatever order you see is fine. Right? Causal consistency. Okay? There are lots of other models. I'm not going to go through too many of them. There's one called Fifo consistency that says writes from a process are seen by others in the same order. Okay, so in this case, you're only ordering writes from a single process and sending them in FIFO order. It's like sending over a socket, but you do not actually worry about writes from other two different processes and how to interleave them. Okay? So that's called FIFO consistency. But even FIFO consistency tends to be too strong in terms of implementation over it. Okay? So what many of these systems do is that they don't actually use most of these models unless there's a good reason to do this. They use critical sections to order when things become visible. Okay? And that essentially gives us what is called entry and release consistency, which say, let's not worry about what order things are happening because that's too complicated. Okay? We will essentially think of these things like transactions. So when you're entering a A critical section, let's make everything consistent. You enter, and then while you are in the critical section, you will hold locks. And then when you exit, again, you make things consistent. But inside a critical section, you don't keep sending writes to all other processes. You only do this at critical section boundaries, which reduces the overhead of sending lots of messages. But otherwise, if you're frequently modifying some variable, there's a lot of consistency overhead because every write has to be sent to every other replica and so on. Okay, so this is called weak consistency using release and entry level consistency. Okay, so that's all I'm going to say about that. And then here's the only thing that you really have to understand here is what is the ordering from the strictest to the weakest model. Okay, strict consistency is the top. As a strictest consistency model, linearizability is one step weaker. Sequential is weaker than linearizability. Causal is weaker. Then you have Fifo. And then you have these three techniques which are weak, entry, release. They don't even do things at the granularity of writes. They do consistency, provide consistency guarantees at granularity of critical sections. Okay? So those are our consistency models. Okay, so let me do one more thing, okay, which is talk about eventual consistency. Right? So since a lot of these consistency guarantees are hard to provide, many systems essentially take a shortcut and say, let's not provide consistency guarantees at all. Okay? We will propagate updates. Okay? Updates will reach replicas, and eventually things will be consistent. But in the meantime, things may be inconsistent, and that's okay. Okay? That's the approach many systems take. Okay? And there are lots of systems that actually do this. So if you take the domain name system, if you update some IP address for a domain, it may take up to 24 hours for that change to propagate. It's not visible immediately. Okay? Up to 1 day delay. Okay? Same is true in many password databases. Okay? So you will actually, if you know how these password databases work, typically this password database is replicated. We use a technique called LDAP, okay? Lightweight Directory Access Protocol. And there are multiple copies of this database, so that if one copy goes down, there are others available. Okay? Often you might see the following case. You go to one machine and you change your password. Okay? You log into another machine with the new password, the login does not work. Okay? You may say, why? The reason is that other machine is actually talking to a different copy of the password database, and the databases have not synchronized yet. Okay, they synchronize periodically. Every half an hour, they'll say, here are all the password updates I got, and you send me your password. So it's happening periodically. So things are inconsistent for a period of time. But eventually, things get back in sync. Okay? That's the idea of eventual consistency. Okay? It's widely used. So if you use any of your cloud storage system, you'll see the same thing. Okay? You make a copy to Dropbox, or it may be OneDrive, or it may be iCloud. It's not instantly visible. And if you have two machines, you make a change here, it will take a while for that change to show up there. In the meantime, it might see an older copy. The reason is these replicas are not synchronizing as if they want to keep things strictly consistent. They're using eventual consistency. They'll say, I will send your changes after a period of time, maybe 5 seconds, 30 seconds. Every so often, you just say, here are all the changes to file. Okay? And then it eventually shows up at the other. So many practical systems, because consistency guarantees are hard to provide, go down this path of eventual consistency. This is not done in things like relational databases, where if you allow this to happen, you might have bad results where you maybe give the same seat to two different passengers because both of them booked on 2 copies of the database. Now you basically created an inconsistency. That you don't want to happen. But for many of these other applications, it's okay. So what we'll do for the rest of the class is see how to do eventual consistency. Okay? So the idea here is you have a database, okay? There are updates happening, and eventual consistency says in the absence of any further updates, all the replicas will converge to a consistent state because they'll keep sending their updates to one another and they'll all become consistent. But in the meantime, they will be inconsistent with one another, and that's okay. That's the basic approach. Okay? So question is, how will we implement this? So for all of what I talked about so far, whether it's strict consistency, linearizability, I didn't show any implementation detail. I just gave the definition. Okay? This is the only approach where we are actually going to see how to implement your eventual consistency. Okay? So how do we do this? There is a class of protocols called epidemic protocols that are used to implement eventual consistency. Okay? This is an old idea in distributed systems. Okay? Originated in the 1980s, okay, in a system from Xerox called Bayou. Okay? So the basic idea of Bayou was that you have, it was really early days of mobile computing. Okay? You have weakly connected machines. Okay? You make a change to a file. How do I make sure that other users who are using that same file or the server gets access to it? Okay? That's mobile computing in wide area. And in those days, okay, you didn't have broadband connection. Most of your internet connection was to dial-up modems. You had to actually connect over a phone line to a server and then exchange data. So it was not like machines are mostly connected like that today. Okay? So consistency was much harder to provide. So they came up with this idea of doing this using providing eventual consistency using epidemic protocol. Okay? So epidemic protocols is actually based on how diseases spread, which we all know because of COVID. Okay? So essentially the idea is you have contact or you are close to one another, you might infect someone else. Right? So the idea here actually is to infect, as not to not infect, which is what humans should do. But these systems are trying to infect other replicas. So as soon as you make a change to a data item that's called an infected data item, you want to spread it as quickly as possible through the system. Okay? And the faster it spreads, the more consistent you get. So goes the idea of epidemic protocol. So you're essentially going to do this. Now, what does epidemic protocols have got to do with this? Okay, you will essentially do what is called pairwise exchange. Okay? Two replicas talk to one another, okay? And they try to infect one another. Okay? It's like you go and you shake your hand with a friend and you spread your germ. That's the same idea, okay? Which you shouldn't do, by the way. But here we want to do this. Okay? So the two things you need to know is we'll call a database or a store infective if it has an update it wants to spread. And if we call it susceptible, which means that it has not yet seen that change. Okay? The question is, what is the best way to spread these updates in the system? Okay. So we'll talk about two different protocols for implementing epidemics. One is called anti-entropy, and the other is called rumor mongering, also called gossip protocol. Okay. So anti-entropy is a randomized protocol. Okay. A replica P is going to pick a replica Q at random. Okay. And the two of them are going to talk and say, what changes have you seen? Here are my changes, okay, since the time T. And they say, what changes do you have since time T? And then Q sends your changes, okay? And then you synchronize. Okay, so you can do push only, pull only, or push pull. If you do push only, okay, then you only push your changes to the other entity, replica, but you don't pull from that replica. Okay? If you do pull, then you connect to some random node and say send me your update. And if you do both push and pull, you do what I said. You say here are my changes, send me your changes. Okay? And then you synchronize. This, by the way, is widely used because that's how Dropbox and many others actually work, because you have a cloud storage, you have each devices that connect to one another, and your machine uploads changes to the server. It then downloads from the server. So it's effectively doing exactly this, except there's not picking nodes at random. You know which nodes where your Dropbox server is, and that's how you do it. Okay? So the basic idea is this is essentially a randomized protocol, and you're randomly spreading your epidemic through the system. Okay? There's one approach. Okay, I'm going to come to why push-based is good or not in just a moment, but let me talk about the other approach, which is called rumor mongering. Okay? This is also called gossip protocol, which is a very well-known class of epidemic protocol. Okay? This is essentially how you gossip and spread a hot news item to somebody else. Okay? So what would you do? If you essentially get an update that's like a hot news data item that you want to spread. Okay, so you are going to essentially contact a node Q and then see if that node has gotten that update or not. If it has not gotten that update, you are going to push and then continue. Okay? And then if you see that nodes have already seen the data item, you back off. Okay? This is how you are going to spread gossip. Right? You have something you want to share, you start calling your friends saying, did you hear about such and such? Okay? And so long as your friends have not heard about it, you'll continue to do this. But after a while, everybody's heard about it. I say, I'm not going to keep calling people. Everybody knows about this news item. So you stop spreading that gossip. Okay? So that's called rumor mongering. Okay? So essentially, if it's a hot item you keep spreading, eventually it becomes cold because almost everyone has seen it. So then you stop spreading. Okay? So every time you contact another node and you ask them if they've seen the update or not, if they have not seen it, you push and you continue. But if they've seen the update, you toss a coin. Okay? And with some probability P, you say, I will not continue to spread this gossip anymore. Okay? So it's probabilistic. So the backoff is probabilistic. It's not like the first node you see, as soon as they've seen the data item, you say, I'm going to stop. Okay? You toss a coin and you say, should I continue to spread or not? Okay? With some probability P, that's variable. And then if the answer is no, you continue the spread. Answer is yes, stop, then you just back off. Okay? Completely randomized. Okay? So now, so both are randomized protocols. So let me go back to anti-entropy. Okay? So I said you can spread by push, you can pull, or you can do push and pull. And it says a push-based approach, it does not help spread updates quickly. Okay? So why is that? Because this is randomized, so initially you are the only node in the system that's seen an update. No one else has seen it. Okay? So any node you contact, it will see that update. And remember that those other nodes will also start spreading that update because you can keep having multiple nodes spread it. But very soon, when most of these nodes have seen the update, then if you keep contacting nodes, they've already seen it. So there's nothing to spread. There's only a small number of nodes in the system that haven't yet seen it. You don't know who they are. Okay? You are picking nodes randomly. So it's very likely that you'll keep picking nodes that have already seen the update. Okay? So to converge to having all the nodes seeing it, a pure push-based protocol will not work. Okay? Because after a while, you will have a small number of nodes that have not seen it, that they will essentially never see the update. Okay? Same is true, that property is actually expressed in rumor mongering for that same reason. Because that is how you are going to spread gossip. After 10 friends say, yes, I already heard this 1 hour ago, you're not going to call another 10 people saying, have you heard this? Have you heard this? Because you will assume everybody knows it, even though there may be some small number of friends of yours who not heard that gossip. Right? So there's always a probabilistic small chance that, which is expressed by this quantity here, that says that hey, you will never actually spread some update to some small number of nodes. Okay? Depending on the value of k, which is how aggressively you back off, that value can be very small or a little, not that small. Okay? So because rumor mongering is a push-based protocol, you are pushing gossip to other friends. Okay? The same is true in anti-entropy. Okay? Initially, it's very good to spread because no one has seen this update. But after a while, it gets harder and harder. Okay? So if you combine push and pull, that's the best of all worlds, because there are some nodes that are trying to pull. So a node that has not seen the update, okay, will contact another node at random and pull that update. Okay? So if you combine both, okay, the chances of not seeing it will start going to 0. Okay? But if you have only push or pull, it will take some effort to ensure that your update spreads to all the nodes in the system. Okay? Yes, question. Okay, question is, if a node is trying to pull, how does it know what is hot and what is cold? Is that your question? Okay. So first thing is, let's distinguish between you're trying to only spread one change to a data item, or you spread lots of things together. Okay. So let's take the case where you're only spreading one change. So in this case, if you're doing rumor mongering, it's a pure push. You're not pulling at all. Okay. So that's how gossip is. You don't call your friend and say, do you have any gossip? That's not how gossip works. Right? You basically ask, they will call you. So it's always push, right? So in the push-based protocol, you are essentially going to have probabilistic backoff. You call somebody, they're not heard what you want to tell them. You tell them you feel good. You call the next person and call the next person. After a while, you start reaching people, say, okay, I already heard about this. Every time you see this, you are going to back off with probability 1 over k. Okay? And then if you basically toss a coin, if it says heads, you stop, you say tails, you continue. So if heads means you will stop. Okay? At that point, whoever is within your friend circle who's not heard this won't hear it from you. Maybe there are others spreading the same gossip. Okay? So there's always some small chance that you will never see an update because nobody called you. Okay? But if you are in anti-entropy, you can actually pull. Okay? You can contact another node and say, do you have any updates I have not seen? In this case, if you are the node that never saw the update because randomly at some point in time you just ask another server, okay, I have not seen anything since noon. Do you have any changes since noon? And then if that gossip had already spread to other nodes, you will actually pull it. Okay? So if you have combination of push and pull, that's a better approach for eventual consistency. Okay, so the question is, in the only pull model, what happens if you're an only pull model? Okay, node P is going to contact Q and say, I have not seen any updates since noon. Do you have any new updates since noon? And then you pull. If you are seen, you don't push at the same time. Okay, you will have to wait to be asked. Okay. The pull based is you just basically contact some other node and ask them to send you any new things that you are not seeing. In push, it's the opposite. You contact another node and push any new items you see. And if you do both, you do pairwise exchange. Okay? So you're essentially going to connect and do this. So if you have many of these mobile devices, they essentially use pairwise exchange. They do both push and pull. Right? So you might have, let's say, a Fitbit. Right? So the Fitbit is periodically going to contact the phone, okay, and push whatever data it has to the phone. That's push. Okay? But there may be other updates that it receives from the phone as well. Okay? Maybe it receives weather information, other things that are then displayed on your device. So you're essentially doing both push and pull in that case. Okay? So this approach, although it's presenting in abstract, actually widely used in cloud storage. It's widely used by mobile devices. This is in the old days, you actually had to take your phone and you had to connect it to your machine and then upload all your songs through iTunes. Right? So that was pairwise synchronization. So any changes you make, first of all, you can download songs, that's just pull. But if you have a playlist update that you made on your phone, it would get pushed to your machine, or vice versa. You made a playlist update there, it would get pulled from your phone. Okay? So all of these synchronization protocols you see for devices, cloud, they all use Epidemic Protocol. Okay? Now, clearly, in some of those cases, it's not random. The user is connecting the two devices. Okay? But you can, if you have n nodes, this is how you are going to do it. Okay? But you can also do between any two devices that you own. Okay? That's not random, clearly, but it uses the same idea. Okay, that clear? All right. So one thing I want to mention in case of epidemic protocols is updates to data items are easy to spread. If you have new data items or new files, that's easy to spread, but deletions are actually very hard to deal with. Okay? So let's say you have a file that was actually made consistent using epidemic protocol. After a while, you delete this file. So let's say it's Dropbox. So you delete this file from your machine, that is from your Dropbox folder. Okay? So now your machine goes and connects to the server and says, what files do you have? Okay? And it will see that you don't have this file, but it's still on the server. So it might think that you never had a copy of this file and you download it again. Okay? Your deleted file has reappeared. Okay? That's not what you intended, okay? Because you just deleted the file. Your machine just connected to the server and said, let's look at what files you have. Let's look at what files I have. I don't have that file. You don't know that user deleted it. You bring it back. Okay? And you regenerated a deleted data item, which is not what the user had intended. Okay? So what this means is, in epidemic protocols, if you delete a data item and leave no trace of it, there is no way to figure out if you never had it in the first place or the user deleted it and hence you don't have it. Okay? So you have to have a way to distinguish between deletions and actually not having the file from the first place. So for that, what you are going to do is you are going to create what's called a death certificate. Okay? When you delete a file, you are going to keep an extra piece of information saying file T was deleted. Okay? So now you know that's an update to the file. A deletion is actually an update. So in this case, you can previous one. So in this case, you can actually figure out whether the item is deleted or not, and you can have the death certificates actually spread through the system. Okay, and that way you know all the machines will start deleting it, and your data item is not going to actually appear after a while. Okay, so deletions are handled by removing the file and keeping a record saying this file was deleted. So you can make a special file saying file foo has been deleted, and that deletion is going to spread through the system. Okay, but eventually you will need to clean up your death certificate. You'll have lots and lots of deleted file over the years, and you'll have all this extra information in the system. So you've got to go clean it up. But until all the copy of this file has disappeared from the system, you have to perform this operation. Okay. All right. So I think I'm done for the day. If you have any questions, I can take them. Otherwise, we'll stop here for today. Any last minute questions about this? Okay. So let's end it here, and then we'll continue next time.